A to BC. And so yeah, let me make this like a tall trapezoid. Where's my parallel? Oh, yeah, what's parallel to what? It doesn't really say. Is AB parallel to CD? I'm just going to assume that for now. I think that's how it works. So I'll just assume AB is parallel to CD. And so AC and BD intersect at E. I keep forgetting to maximize. Oh well. There's AC, and here's BD. And they intersect at E. And P and Q are the feet of the perpendiculars from A and B to the opposite sides. Okay, so ABPQ is cyclic. And I wish there was a way to do altitudes in GeoGebra. You have to do it manually. So okay, we'll just draw the circle just for the heck of it. And you draw the circumcircles of CEQ and DEP. Let me make it so I can see where they intersect. This is a tricky, okay, something like that. And if they intersect at F, we want to show that AP, BQ, well, AP and BQ intersect at this point. So I don't know if we could use Michel's theorem. Basically, we want to show EF and that point are collinear. So we want to show G lies on the radical axis of those two circles. So maybe we could show it has the same power with respect to them. Let's see, BPE and CEQ. We want to show G has the same power with respect to both of those. One sec, guys, I'll be right back. All right, thanks for waiting. Let's see. So I see we have a comment here. I think we can extend AB and BC. Let's try it out. So if we AD and BC, they don't meet on the circle, but maybe that'll still help. Maybe it's worth extending PQ and AB. I don't know. Let me draw the midpoint of AB. So that would be the center of that circle. Applying radical axes on some circles can show this. Let's see. So what are the right circles to do that? Are G and E isogonal? That would be interesting. If that were true, it would be like Serbia would be like obsessed with isogonal problems. Because I think there was a problem on the Junior Balkan Math Olympiad that was, okay, they're not isogonal. Well, that almost looks, is that really only 13 degrees? Interesting. Okay, so we want to show G, can I extend AP and BQ to meet the circles? Yes. But it's, yeah, we want to show, we just want to show G has the same power with respect to them. Yeah, so I guess that kind of makes sense, right? You want to show that GP times, so GP times GJ would be the power with respect to one of them. And then for the other, which I have to make room for, what's the best? Maybe something like that. So, and are H, J, and K collinear? I don't think so. But you want to show G has the same power with respect to them. Yeah. Okay. Maybe we could draw the centers of those circles. I don't know how much that would help. So we know G has, so GQ times GB is GA times GP. So I think we want to show, is KJ, we want to show maybe that KJ is parallel to CD and AB. Yeah. That's basically what we want to show. We want to show CD is parallel to both of them. I'm sorry, JK is parallel to both of them. That would solve it. Okay, how would we show that they're parallel? Which is the same, I think, as showing that KQPJ is cyclic. So yeah, a lot of equivalent things. Because if we could show that, then it would be the radical axis theorem, right? So how do we show that that's cyclic? Maybe phantom point. So what's the right phantom point to use, I guess? Oh, draw the parallel through K and let it meet the other circle at J. Okay. So I could hide this, maybe. And then I want, if I call, I want to show that I could call this J prime, I guess. So I want to show that these are collinear. It's an interesting idea. What if I did this? So what if I labeled these 2 points right here? What if I drew both parallels? So like this, and then I want to show that these 4 points are collinear. So instead of J, I could call it M. And I want to show J, K, L, and M are collinear. So I could show like the distance. So I know that QKJ is similar to QAB, and I know that LPM is similar to PAB. If I could show, I want to show that the sum of the distances from Q to those 2 triangles is the same as what it is for P. And I wonder if that's just like a calculation. I think it should be. Yeah, I think it should just be a calculation. I'm just thinking the best way to present it. right? Also, we know HQGP is cyclic, but so what if I try writing it like this? So so I'm just going to do some scratch work here, but the distance from K to the line AB is the distance from that's the distance from Q to the line AB times KB over QB. Actually, yeah, KB over QB. So yeah, this might get a little messy, but and the distance from N to the line AB, or M to the line AB, yeah. There might be a faster way to do this, but I have a feeling this works. Actually, maybe it might be better to use point G for this. No, I don't think so. So all right. And I want to show that these two are equal. So what's KB over QB? So we have GQ times GK. But we have QK over QB. Yeah, how do I get KB? KB is QB plus QK. So yeah. Yeah, maybe this is harder than I thought. Yeah, no, I don't know about doing it this way. So, oh, I forgot. H, E, and I are collinear by Cheva's theorem. I don't know how I missed that. I always remember that. I don't know if that helps. Yeah, maybe I'm making this harder than it has to be. So let me draw this circle too. So yeah, maybe we could use Picard's theorem because H, E, and I are collinear. So by Picard's theorem, let's see. So HE would be perpendicular to NG. And not only that, they would both pass through this point right here. So NG and O are collinear. Actually, that's just a Humpty point, right? And so we want to show G has the same power with respect to those two circles. Trying to use Casey's theorem. I don't know if that helps. Yeah, so what if we drew this parallel line here and we let it intersect PN? Oops. Sorry. What do we say about R? Yeah, so we want to show that this quadrilateral is cyclic. Let's see. Okay, that's fine. What's your solution? I'm going to delete some stuff.
By Rames.
Hold on a sec. Let me just check one thing. Just curious before I delete this diagram. Okay. All right. Let me delete a bunch of stuff and then I will write up your solution. Delete. Are there any lines you want me to keep? So I'll delete that. Let me delete this. Delete this. All right. Hold on a sec. So what's your solution?
By Rames theory, we know that CDPQ is cyclic.
Okay, CDPQ is cyclic. That's an angle chase. Yeah, but or Rames theorem.
Yes, it
Yeah.
is.
Yeah.
Yes, and by radical axis, we know that CQ, PD, and EF are concurrent.
So PD, CQ, and EF. Okay.
Yeah, and we have to just prove that GE and where diagonals concur are concurrent.
Okay. So we have to show that GE passes through that intersection point, right? Yeah. Okay. So basically,
Yeah, and it's we have a theory that is said. Yes.
so we want to show that GE and J are collinear, basically.
Collinear. Yes. And we have 3 points on one segment, 3 points on another line. I have forgotten the name of the theory. I think it was. If you take a look at it, DPC. Yes, it is this one.
All right, yeah, so that does it. All right, I like it. So I'm going to write it up. That's very nice. All right, let me delete some stuff that I don't need. In fact, I think J is the orthocenter of HPQ. I think. Yeah, no, that's actually maybe not. But yeah, your proof still works. So is there anything I can delete? I don't need this circle for the proof. All right. So let's okay. So I'm going to do the angle chase, which is the same as Rimes theorem, but we just have so first I'll point out, this is kind of obvious, but angle AQB equals angle APB equals 90. So AQPB is cyclic. And then we have angle QVP or QDC is 180 minus angle DAB or 180 minus angle QAB, which is angle QPB. Whoops. That means that QDCP is cyclic. or use Rimes theorem. Or Reims theorem, I'm not sure how to pronounce it. And then once we know that, by the radical axis theorem, PD, CQ, and EF concur at a point J. All right. And once we know that, now we can use Pappus. So by Pappus's theorem on the lines DQA and CPB, let me delete some stuff, sorry. I don't need M and N. I don't even think I need H, actually. So DQA and CPB. J, E, and G are collinear. And that means that EF, AP, and BQ are concurrent. I'll do it the way it says in the problem. AP, BQ, and EF are concurrent or parallel. So that would be a kind of a degenerate case. All right. Thank you very much for that solution. Let's see. Oh, I got to add this. And I will draw the final segment. Very nice. Let's move on to the next one. We have about an hour left here. All right, so we have a triangle ABC. And so I looked at this problem very quickly. So I think M, it's best to draw point M first. So I call this point M. So X is on M. Oh, whoops, M is on AB. So it's probably better if I call this A and this B and this C. And then we want AM is equal to MX and BY. Wait, AX is equal to MX. So yeah, so draw the perpendicular bisector of AM and draw the perpendicular bisector of BM. And then these are points X and Y. So that's X. This is Y. And maybe I'll just draw these points just to make it easier. So the midpoints of AM. All right. So if I hide this and this, there we go. All right. So those are isosceles triangles. K and L are the midpoints of AY and BX. That's interesting. So this is K. And this is L. And O is the circumcenter of ABC. All right. There we go. And then we reflect O over K and L. We call it O1 and O2. Oh, this is reflecting over a line. I want to reflect over a point. So I reflect O over K and O over L. And they're calling it O1 and O2. And we want to show that XY O1, O2 is cyclic. Okay. Let's see who's here. Okay, I think we only have 3 people left on it. Yeah, we still have an hour, so sometimes people pop on at random times. That looks good. So K and L are, okay, so yeah, we're reflecting. I should draw probably these 2 segments. So are O2Y and E collinear, or is that a coincidence? Yeah, O2, I think it's easy to show that these are collinear. I think it's just a length chasing, and that these are collinear. But wait, that wouldn't make sense. That would mean that XY O1 O2 is a trapezoid. So we actually want to show it's an isosceles trapezoid. I think that's true. I think that's right. We actually want to show it's an isosceles trapezoid. It's kind of silly. And that almost doesn't seem like it should be that hard. So basically, I wonder if that's just like a length batch. Because if we, whoops, if I draw the midpoints here, so I draw the midpoint of XO1 and the midpoint of O2Y. If we could show that FG is parallel to AB, that would solve it. And that might just be a length bash. I think it is. Let me start writing this up. But I think it's just, yeah, showing it's an isosceles trapezoid. Of course, GeoGebra made this a lot easier, but so first, we want to show XO1, and so let B and E be the midpoints of AN and MB. And it might be good to draw the midpoint of AB. So I'm going to do that. I think that'll help us a little bit. H. Let H be the midpoint of AB. All right. Okay, so basically we want to show that x01 and b are collinear. So what is K? So K is the midpoint of AY. So yeah, I mean, we could drop the perpendiculars from K and L. Maybe we could use parallelograms, right? So AO1, YO is a parallelogram. Trying to think, what's the most elegant way to explain this? So yeah, AO1, AOY01 is a parallelogram. So, right, like let's just do this. So, but yeah, it has to be a length dash. So we want to show that okay, so I think I've got it. So first of all, let me hide. Where are we? Let me hide these two. So since AOY01 is a parallelogram, the distance from A to the perpendicular from O1 to AB is the same as the distance from O to YE. So okay, so yeah, I don't even know if I need H here. It's just by symmetry. So the diagonals of AOY01 are a parallelogram. Oh, bisect each other. So that means that AOY01 is a parallelogram. And then similarly, BOY02 is a parallelogram. BOX02 is a parallelogram. All right. And once we know that, I'll write it this way. Let L be the line through O1 perpendicular. I don't know if this is the fastest way to write it out or express it, but we would have the distance from A to L is the same as the distance from O to YE. So we would have the distance from O to the line YE, where denotes distance to a line. All right. And what was I going to say? So the distance, and then, okay, so we want to, but we want to show that's the same as dm, right? So the distance from O to YE is the same as the distance from O to YE is AB over 2 minus EB. So this is let me move this to another line. And then similarly, so that's AB over 2 minus EB, which is DE minus ME, which is DM. So, oh, I should actually put this down here. Yeah, this is a little awkward, but I don't know if I'm expressing it the best way, but it works. So this means that XO1 and D are, but what are F and G, by the way? I don't even know what F and G are. What did I do with F and G? Oh, I'm going to use them later. Okay. So XO1 and D are collinear. And similarly, O1, Y, and E are collinear. And then let F be the midpoint of XO1 and let G be the midpoint of YO2. So I'll say that just in one line. Let F and G be the midpoints of XO1 and YO2. And then we want to show FD is equal to GE. I'll say, and right here I'll say, and YE is parallel to XT. Okay, so O1D, we want to show FD is equal to GE. So FD is O1D plus FO1. Well, let's see. We have what's the best way to do this? FD is XD minus XF, which is XD minus FO1. You know what? There's an easier way. Okay, so let me drop a whole bunch of perpendiculars. This is kind of silly, but I'm pretty sure it works. So okay, so O1B is equal to 2KH minus OI, which is YE minus OI. Write like this. And then similarly, O2E is XD minus OI. O2E is
Michael. I thought that if if x01 and d is collinear, so and so on with O2 y and e, so we just need to prove that I01 is equal to x02, right?
So x02, yeah, y01 is equal to x02.
Yeah,
Oh, but
but,
they're both
y-
parallelograms. So
Yeah,
O1y is AO is BO. Ah, I like it.
yeah,
Okay. I made it more complicated than it had to be. All right.
yeah,
That's pretty nice.
yeah.
All
But
right.
the one you prove that x01 in d is collinear. That's great. Yeah.
Yeah, so I still had to do that. So it doesn't get rid of the whole proof. So
Yeah.
but still, that's a nice way to finish it. So then XY01, O2 is an isosceles trapezoid. So it's cyclic. All right, let's see if we can finish off the last problem. So yeah, let me just check that I wrote this out all right. So yeah, we don't need, let me delete H, I, and J. We don't need them. All right, so I'm gonna move on to the last one.
Yeah. Okay. Okay.
All right. Let's see. Yeah, that was a fun one. So we have an acute triangle ABC, and M is the midpoint of BC. And yeah, if we solved this one earlier, we can go back to the other one. So this is point M. D, E, and F are the theta altitudes. And H is the orthocenter. So D, whoops. D, E, F, H, and S is the midpoint of AH. So that's basically the center of that circle through AF, H, and E. So I think it might be good to draw these two circles. So S is the center of this circle, and M is the center of this circle, and MS is perpendicular to EF. G is the intersection of FE and AH, okay? So there's probably some isogonality things with G. So yeah, maybe we want to draw the orthocenter, the circumcenter of ABC. Let N be the intersection of AM and the circumcircle of BCH, okay? So the Humpty point, right? Actually, I'm not sure if it's the Humpty point. I think it is though. Yeah, it's the Humpty point. So basically, it'll pass through this point, I think, right there. Yeah. So this is well known that these all concur. It's like video 5 on my channel, I think. and they want to collect n, and we want to show that HMA is equal to GNS. This looks like it might be easy. I'm not sure. So let's see. So yeah, we know that, so this is perpendicular. And so HMA is, so yeah, maybe we could use Ricard's theorem too, because basically EF, HN, and BC should concur. So I proved this in video 5 on my channel, but it's pretty easy. And so HMA is, that's the angle between HM and MA, but we know, let's see. Okay, maybe it's not that easy, because G, it's not that clear how to use point G. But let me draw the circumcenter of ABC.
Yeah, Michael.
Mm-hmm.
We note that GD is harmonic.
Okay.
Yeah. So if S is the midpoint of AH, so SG times SD equal to SH square and equal to SN square. So the triangle SNG is similar to triangle SDN.
SMG is similar to
SDN.
SBN?
DDN, yeah.
SDN.
Yeah.
Okay.
So the angle SNG is equal to SDN and equal to HMN.
Okay. So yeah, that does it. All right. So I added more lines than I needed. But I like how you use that lemma about harmonic conjugation. So I'm going to write it up. Oops. Let me hide a bunch of things. Just make it look nice. So yeah, I'm going to delete these 3 lines right here. But yeah, that lemma about harmonic conjugations where SH squares SG times SG, that comes in handy a lot. And so once I write this up, then I'll go back to that problem that we didn't solve. All right. I'm going to make these segments instead of lines. Okay. Did we even use that BHNC as cyclic? Oh, actually, maybe I wanted to draw those lines. Well, yeah, to show that this is in harmonic conjugation. Let's see. Yeah, so I'll just say A, D, B, E, and CF concur. So A, H, G, and D are in harmonic conjugation. But first, let me say, so yeah, did we ever use that BH? Oh yeah, because we needed that because we were using that HD and M as cyclic eventually. So but I don't think, I don't know. I don't think, 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 Yeah, maybe we don't need this circle. I don't think we need this one. Okay, so whoops. Let me hide that circle instead of deleting it. So we have HN is perpendicular to AM. And so HNDM is cyclic. All right. And once we know that, we have A, B, B, E, and CF concur implies that means A, H, G, D are in harmonic conjugation. And S is the midpoint of AH, implies that SH squared is SG times SG, SG times SD. And once we know that, so I should say Sn squared is equal to SH squared. And once we know that, let me close this. So that means that triangle SNG is similar to triangle SDN. And then we have, from there we have angle GNS is angle SDN is HDN. HMA. All right. I think, let's see. So GNS is SDN, is HDN is HMN, it's HMA. Very nice. All right, so let's see how much time we have. We still have 15 minutes, so we can go back to that problem that we didn't solve yet. And see what we can do. So do you have another solution to this problem? So yeah, maybe we didn't need projective geometry. Maybe there was like a way to do it without that. Do you have another solution?
Yes, this one was awesome actually, but yes, we can easily see that AHE, AHN is equal to NMD.
So AHE and ANE are equal to angle, what do you say, AMD?
AHN is equal to NMD.
Yes, yes.
So AHN is equal to SNH because SHN is isosceles.
Okay. So
S and H is equal to NMD. We just need to show that I and G and H is equal to HMD.
okay, I think I see what you're doing. So we have S and H is AMD. And so we need to show therefore that G and H is HMD, right?
Yeah.
Okay.
And then we have to draw the circumcircle of AFHE.
Okay. So, all right.
And then we let MH intersect it at I.
NH.
Yes.
Intersect BC or intersect.
No. HM intersect the circle at I.
The big circle or so like right here.
No. The circumcircle of AHN.
Oh,
The circumcircle of AHN.
But that just intersects. We want to let this circle intersect. HM. I'm sorry. Say it one more time.
HM.
HM. Okay.
So HM intersects.
Okay.
At a point, and then what we just need to prove is that NG and I are collinear. Then by angle chase, we will get a result.
Okay. And to show those three are collinear, is that Pascal's theorem or something? Let's see.
Yes, I think it is Pascal.
Okay. It looks like it.
And we're done.
So,
but this one was awesome. That the solution that you have written was really, really good and easier.
Yeah, I think it is Pascal's theorem because I think ME and MF are tangent to that circle. That's like well known, right? So I think so basically it's like Pascal's on AFFHEE. So FF meets well, actually, hold on a second. No, AFFHEE. Yeah, because FF meets EE at M, and then HM. I think it works. I haven't thought it all the way through, but I think so. Because our
yes,
audience
we can return to the problem that we did.
Yeah. All right. Yeah. So I'll go back to the problem that I did originally, but yeah, I'm pretty sure there's a way to get that to work to show that I, G, and N are collinear.
For a minute, could you explain the lemma SH square equals to SG dot SST? Could you name that lemma?
Yeah, I don't know a name of it. I've just seen it on AOPS a lot before.
Michael, as I remember, this called Newton or Maclaurin, yes.
Newton-Maclaurin.
Newton-Maclaurin. So hold on, I'll type in the chat. Newton-Maclaurin. Something like that.
Yeah, something like this. Yeah.
Interesting. Yeah, I proved it once a while back. So yeah, you can. So basically, I use the fact you have to use the fact that AH, G, and D are in harmonic conjugation. So these two facts together mean that SH squared is SG times SD.
I got up to the uh, concurrent part, and after SH square, then it blew off.
Yeah, this step right here, right?
Hmm.
Yeah, that's the famous theorem. So yeah, Newton-Maclaurin is what Fung says it's called, right?
Do you have a small proof, or is it like a big proof?
I'm not sure. Whoops. I proved it a while back. I don't remember the whole proof. I don't know
Sure.
if there's like an elegant way to prove that. Um, yeah, I don't remember, but it's a good question.
No, you could easily prove that just by calculate. Yeah, easy calculate. We have that GD is a harmonic conjugation. So we have AG on AD is equal to HG on HD. So we just need to do some calculation. So we have the HN square is equal to SG times HD.
Yeah, it's in the end, it's just like a long calculation.
Okay. It's just from the harmonic conjugate, right?
Yeah,
Yeah.
I think there
Okay,
might
thanks.
be.
I will check it out.
Yeah, try it out. I think there might be more elegant ways to prove it where you don't have to. I think I remember seeing a geometric proof that doesn't use any calculation, but I think I posted on AOPS also a proof that uses a lot of calculation. So yeah, see what you can figure out there. I guess it's the same as saying that SE is tangent to that big circle. Yeah, so I mean, in this case, actually, in this case, I think that there's a way around it, because basically we want to show SE is tangent to the circle through BFE and oh no, it's not that easy, sorry. Because we want SG times SD. Yeah, check it out, see what you can find. All right, we have just 5 minutes left, but let's just see if we can think of any other ideas for this problem.
Yeah, I have an idea for this.
Okay.
Yeah. So we just complicated it so much.
Yeah.
So yes. It's okay if you don't need to erase. Yeah. So we have that MA is equal to MK, right?
MA is equal to MK. Yeah.
It's equal to MI too.
Okay. Yeah.
Yeah, and so on LD is equal to LI.
Yes.
Yes. So
yes.
we have to need to prove that XM over XL is equal to IM over IL.
XM over XL is IM over IL.
Yeah. So yes, and we have that the triangle XAB is similar to XDC.
Oh, wait. So wait, I think it might be, kind of easy. Yeah, so basically we could show XI is the bisector of X.
Yeah.
Okay.
That's correct. Yeah.
And then once we know that, can we show angle L? We also know angle LXC is equal to angle MXB. So
Yeah, we just have to know and yeah. So, from
solve it?
yeah, that's all it. That's all this.
Okay, let me write it up. So basically a spiral similarity takes I still wonder. So let me write out what we have. So a spiral similarity takes XAMB to XDLC.
Yeah.
And or let me write it like this. Okay, so XM over XL is equal to MK. So yeah, so XM over ML, that's equal to, I'm sorry, XM over XL is MK over IL, or KM over IL. Which is KM over IM. And so that means that XI bisects angle LXM. And then if we could show angle, I think we need to show from there that angle CXL is equal to angle BXM. Oh, that's true by the spiral similarity. So but wait. So we know that XI bisects LXM. We want to show it bisects AXC. So we want to show LAX equals, hold on, give me just a second. We want to show LAX.
We need to prove that XI is bisects angle AXC, right?
Yeah, we need to show XI bisects angle AXC.
Yeah, but XI bisect angle LXM.
So we need to show LXA is CXM, right?
Yeah. Yes. So but the angle MXA is angle to LXC. So if we let LXC minus LXI and MXA minus MXI, we have that AXI equal to CXI.
Okay, so it looks like we have LXC is DXL is AXM. So hold on just a sec. So DXL, which is angle AXM. And so if we combine the above two, then xi bisects axc. axc, and therefore xa and xc form the same angles with the tangents from x to k, and that's it. All right, so that solves it. All right, so we have finished our session today, and we ended up, so yeah, we just finished it and we got through all the problems, which I think is pretty amazing. So we are out of time, but thanks everyone for watching on YouTube. This was a lot of fun. So I will see you next time. And as always, if you want to join me, feel free to email me at mgreenb801@gmail.com. The sessions are at 10 a.m. on US Central Time. Have a nice day.